Hi, my name is Sam. I'm on a mission to make transport sustainable using the power of steam. I'm quite excited to announce a project that's been ticking along in the background since the inception of the Rail Loco, and I've now just decided to prioritise it a bit more. Looking at what I've got behind me, you can possibly guess where I'm going with this one. And I gave a couple of hints in the last few episodes. The Rail Loco and rail is very important in the future. It's going to play an important role in sustainable transport. But rail is only a part of the equation. How do we grow food in the future? How do we move goods and people around on the roads? Because rail can only reach so far. Immediately that has me looking around thinking, well, to make road and agricultural transport and cultivation sustainable, we need to use wood fuel. And how can I use wood fuel in a road vehicle, in a truck or a car or a tractor? At first look, it sounds very impractical, but of course it's all been done before. What is a traction engine? It is a very elegant, solid-fueled machine for transportation and agricultural purposes. So then it's a matter of, could that concept work today? And if it could, what would it look like? How would it be designed? And what are the main reasons that traction engines fell out of favour? But today tractors for agriculture need to have a 3-point linkage, and they're very different to what a traction engine was. So what I'm going to begin building is an agricultural locomotive, or an ag loco. And whilst it's not exactly a traction engine, it is really a traction engine, but a very modern version. One that is going to meet the needs of modern farmers and modern transportation. So for starters, it's going to have pneumatic wheels, and it's going to include all of the advances in modern steam technology that were developed by Porter and are going to be applied to the rail loco. But not only that, the ag loco is of course going to include the new boiler technology, and that's most important because this boiler technology, as I explained in the last video, is lightweight, it can't explode, and most importantly it doesn't emit sparks or smoke. So especially where the ag loco is working in a dry field of lots of tinder-dry grass, you can't have a conventional traction engine rolling around in there throwing sparks left, right and centre. It'd be an absolute nightmare. So the elimination of spark emissions, or emissions completely, with this boiler is key to the ag loco being successful. So a lot of the technology that the rail loco is going to include can be tested out on the ag loco, which is a great opportunity to learn a lot more about some of the finer details of the cylinder design and the overall system working as a whole. It's going to help me a lot to get the rail loco spot on, and it's also going to give me a tool with which I can show people just how well modern steam works and just how different it is to the conventional steam that we're all accustomed to. I'm actually going to base it on the highly successful Massey Ferguson 35 tractor, because that design of tractor and the TEA 20 before it really represented the beginnings of the modern tractor as we know it today. So it's a nice place to start. It's small enough to make it feasible and cost effective and realistic to build. To learn a bit more about the design of modern tractors, Philip and I took a bit of a tiki tour around some of the best ag dealers in Canterbury to have a look at modern tractors, understand the features they've got and how they're designed, so that I can make sure I'm designing the ag loco to suit the needs of modern farming. Of course, the ag loco is going to be completely different to a modern tractor that we're all used to, but the important thing is that it can match or improve on the performance of a modern tractor without burning fossil fuel.
So that's hydraulic with some sort of reservoir to let it bounce. Because obviously hydraulic doesn't bounce. So it's got a tank with
accumulators.
You can adjust the ride height from the cab or not?
You can drop the suspension down from in the cab.
Are some tractors better than others for front suspension?
So this is a Massey front suspension. So I'll show you a few. When I first started in the industry, the average horsepower was like 90 to 100 horsepower.
That's
now the average, now the average horsepower is like 120 to 140.
But this is a huge tractor.
280.
Yeah, it's just insane, isn't it?
But these Fence are the Rolls Royce tractors.
Right. Are they the most expensive?
Yes.
Right.
So this is a Fence suspension, so you can see it's all linked backwards. And
It's fully floating.
yeah. So PDO drive, you've got 540, you've got 1000, and on some Fence you've got 750. So
It's got speed sensors all over the place, hasn't it?
The great thing about basing the prototype ag loco on a Massey Ferguson 35 tractor, you can buy all of these parts off the shelf. So these are the front stubs and steering spindle and the front hubs, all so much more cost effective than I could ever dream of making them. And unlike a traction engine, this is going to use a modern roller chain drive, and this actually has a lot of advantages. I keep hearing that it's going to be noisy, but if I'm careful about how I design it, it should at least perform as well as the gears on a conventional traction engine would, and all of the sprockets are again available off the shelf, so that just saves an enormous cost. So it's 1 1/4 inch pitch roller chain, and it's going to have 19 tooth sprockets on the crankshaft, and this basically will drive from a 19 tooth sprocket down to I think it's a 45 tooth sprocket, and that's actually going to be on the rear axle. So the neat thing is that whilst it's going to be set up to achieve a speed of 40 kilometers an hour on the road, if it's desired to achieve a higher tractive effort or a higher drawbar pull, a larger sprocket can be mounted on the rear axle. That gives a lot more tractive force without increasing the load on the roller chain, which is quite a unique facility. You can't do that very easily with gears. Like with the other parts, I'm using standard Fergie 35 front and rear rims, following the suggestion of the supplier, because I foresee the prototype spending most of its time on the road. I've had truck tyres fitted to the front wheels, should wear a lot better on the road. And again, the rear wheels are Fergie 35 rims, and I've made sure to purchase radials for really good on-road performance. So apparently the radials just work beautifully on the road, don't wear much at all. Some time ago, Dad cut and I pulled this poplar down, and ever since Dad's been pestering me to cut it up, and to be fair, it has been quite a while. So I've got the electric chainsaw here and some vegetable oil to use as chain lube, and I'm going to cut it up. Of course, Dad's donated this for boiler fuel, so I've got to get it around to the workshop, and it should be ready to burn by early next year. I quite like poplar. It grows really quickly, it dries out fast, it's lightweight, easy to handle, splits really easily. So yeah, fuel of the future. I've basically been all week on the drawing board. I did get a haircut, finally, better late than never, and I've almost got the circulating pump details all sorted out. One particular part that took quite a while to get the design right for was the suction and discharge valves. Early on I started off with a large number of small valves, so for each pump there would have been a total of 16 small valves, which wasn't quite as simple as I wanted it to be. So I ended up going for a single large diameter valve, fairly conventional. It looks like it's going to work quite well because I'm not running at really high speeds. That's simplified the design quite a lot. So the valve lid itself is going to be 304 stainless steel, the valve seat's going to be 304 stainless steel, and of course once again, because this pump's running at a high temperature, we have a problem with differential thermal expansion, but in this case I've been able to use that to my advantage. It's a fabricated design, so there's no casting involved apart from the liner. The suction valve fits here and the discharge valve fits here. These are the suction and discharge valve seats, and then the valves as they will actually sit in the pump. So they are fairly simple lids. There are very light springs to close the valves because as the pump is actually mounted, these valves are horizontal, not vertical as shown here. So where I've been able to use the differential thermal expansion of the stainless steel, so these are 304 stainless steel seats, I've got bronze guides pressed into them, and then stainless steel valve lids which operate on those guides. Now I've been able to use the higher coefficient of expansion of the stainless steel compared with the mild steel body to actually hold the seats in place when the pump heats up. So the design is that when the pump is cold, when everything's cold, these will fit into the pump body with almost a clearance fit in the bores. When the pump comes up to temperature, these expand more than the pump body does, and that generates an interference fit to hold the seats in place. That makes it really easy to remove the seats to replace them later on. No special tooling is required. All sounds pretty good in theory. Well, I think it does. So we'll find out soon enough whether it's going to work or not. But I think it will. Of course, you might be wondering, what pumps is he talking about? So if you are, have a look at episode 5, where I finally divulged some of the boiler secrets and explained that this particular boiler uses a circulating pump to pump boiler water around the heat exchanger instead of natural circulation. So if you're not sure, have a look at episode 5. So I've got the drawings done, but I can't give those drawings to a profile cutter because, well, they're just a mess. There's a lot of unnecessary information there, and then the profile cutter has to A, fully understand what he's looking at, and B, try and break the drawing down into all of the component parts and just work out actually how it's going to be constructed. So I've already done all of that in my head while I was designing it. I just have to reverse that and turn the whole drawing into a set of profiles. And because they're two-dimensional profiles, I can simply draw the profile out and then specify the thickness and the material, which makes it simple and easy to follow. But there's going to be quite a few profiles for these pumps. I haven't worked out just how many yet. Just getting started with the profiles for the steam passages for the steam end of the pump. These direct the steam into the main control valve, and then from the main control valve to each end of the cylinder, and then from the cylinder to exhaust. Still going on the profiles, slowly but steadily getting there, up to part 36 now. 44 parts in. I think that's all of them. We have the valve seats, 304 stainless steel. I figured I'd have these water jet cut, saves an awful lot of time on the milling machine. And we have the brackets, or part of the brackets, which support the pumps. So these actually use the same fasteners that attach the centre section of the pump, or the centrepiece, to the steam and water cylinder. By doing it this way, it means the pump can be mounted on both sides of the locomotive with the plumbing connections all facing the same way. Typically when steam-driven air compressors were mounted on steam locos, the plumbing had to awkwardly go, if the steam was coming from the rear of the boiler, had to go over the pump and back to connect with the steam inlet, and the exhaust had to come around and over the top to exhaust up beside the funnel. Doing it this way means that the cylinders can be turned around, so it allows greatly simplified plumbing, which is always a good thing. Because I haven't got an A3 or A2 scanner, which I'd really like to have, but I haven't, so I'm actually drawing these on A3 sheets of paper. I've drawn out the size of an A4 sheet. Doing it this way allows me to clip it on the drawing board nice and easily, and now I've just got to go and cut all these out. Well, that's done. So once I've done all that, this is what I give to the water jet cutter. So on the front page I've specified the materials they're going to need to use and the tolerances to which they'll have to cut the parts to. And each part has a part number, the number required, and the thickness and material from which it's going to be cut. It feels like I've been stuck on the drawing board forever trying to finish off the circulating pump drawings, but I finally got them all finished off. I've sent the profiles out to be water jet cut, and hopefully I'll have them back in a few weeks' time. In the meantime, I've got to try and keep the old circulating pump running that I explained in the last video. And when I first got the pump, it was not working at all well. It leaked a terrific amount of steam past the rings, and a lot of that had to do with the fact that it's got broad rings and there's a lot of clearance between the lands and the rings. So the steam was leaking under the rings and out the other side. What I did was pack underneath the rings with gland packing, and that worked well, really well, but after a few months it would blow out and then I'd be back to square one. In the end, what I decided to do was make new pistons that fit the rings better. That helped but didn't fix it. So finally I decided to put Teflon rings in the pump, and to do that I bought some carbon Teflon sheet, and I actually made split rings by cutting strips and then by hand forming them into rings, putting them in a little jig in the lathe and facing them off, and they've worked beautifully to date. However, because of the design of the pump, at each end of the stroke the piston and the rings cover the exhaust ports and create a cushion zone at each end to stop the piston striking the covers. And I suspect that in doing so it's actually been cutting away the Teflon rings, because it's quite soft and it tends to be soft enough to actually flow into those ports as it travels past them. And my guess is that that's cut a bit of a scallop into the rings. So during the last steam test the pump started to leak really badly, and I just need it to hang in there for a few more weeks, but I'm going to pop the cylinder cover off the pump and just have a look to see if I can see why it started to leak so severely, and hopefully it's not too bad and I can keep using it, but it is using a lot of steam and it does kind of make the boiler a bit tricky to steam, so we'll see what it looks like. So this is the Worthington Simpson circulating pump. You may be able to make out some dates on the nameplate there. It is quite old and it is much too small for the job, but I had to fit a trimming feed lubricator to feed lubricant, cylinder oil, onto the piston rods because when this is in service for pumping boiler water, these glands must be absolutely tight. They can't leak at all. That means it needs to be lubricated somehow. Normally a small leak would be permitted and the water that leaked out would lubricate the rod, but that doesn't work here. So the oil just puts a light film on the rod and makes a huge difference. What I've got to do, I temporarily wrapped this insulation around the steam end as a bit of a test some time ago. So I've got to take that off. The cylinder cover's under here. So I'll pop that off and I'll get in there with a torch and just see how it looks. So having a close look in the bore here, what I found is that the ring gap on the Teflon rings has opened up significantly. So when I installed the rings there was a very tight gap, but the gap is now very large, and I suspect that due to the old and somewhat rough cylinder bores, the rings have just been abraded away quite quickly, being so soft. So I'll put it back together. I think we'll get away with a few more steam tests, and by that time I'm going to have the new circulating pumps finished and on the boiler. A few months ago I engaged a local firm called Motivated Design and Analysis to undertake a peer review of the boiler's safety features. So in the last video I explained that the boiler couldn't explode and that I designed and calculated it in such a way that if the internal water tube pressure system failed catastrophically, it wouldn't exert a pressure exceeding 50 kilopascals on the boiler shell. It doesn't mean much just me saying that, and I engaged Motivated to undertake a peer review of my calculations and my general approach to the safety of this boiler. And last week they came back with their conclusion, and I'm pleased to tell you that they agreed that the analysis that I undertook does indeed demonstrate that the energy released during a potential catastrophic failure would not exert more than the 50 kilopascals maximum allowed by hazard level E classification. So in New Zealand, boilers and pressure equipment under the pressure equipment, cranes and passenger ropeways regulations are classified by hazard level. The regulations actually make no reference to any particular standard for identifying the hazard levels, but there is one standard used in New Zealand which is AS4343, and that standard sets out the procedure for calculating the hazard level of a boiler or a pressure vessel of any sort. Now, when I designed this boiler, I set out to design a full-size boiler that could be classified under AS4343 as hazard level E. And the hazard level classification works by A is the most severe hazard, B is the less severe hazard, but typically most boilers are hazard level B, and then there's C, D and E. And E represents negligible hazard, at which point, generally speaking, equipment doesn't need to be certified or inspected. But AS 4343 actually has a clause in there, not intended to exclude this type of boiler, but it does make it not possible for this boiler to strictly conform to hazard level E. So it's a work in progress. To put you all in the picture, I'll read out the last paragraph of their conclusion. However, motivated design and analysis agree that the thermodynamic steam energy and adiabatic expansion analysis carried out by Macquarie Locomotive Company demonstrates the energy released during a potential catastrophic failure would not exert more than the 50 kilopascal maximum allowed pressure for a hazard level E classification. This suggests that although the Macquarie safety boiler is strictly considered a hazard level C system as per AS 4343 2014, this classification does not account for the additional safety features inherent in the way this particular system has been designed. As such, a hazard level E classification may be more appropriate. This is a great step in the right direction. There's a fair way to go, but in any case, the team at Motivated Design and Analysis, you were great to work with. Thank you, and I certainly hope to keep working with you in the future. We're just lighting the boiler up for our bi-weekly steam test, and it's been 4 weeks now since we made the application of steam to the weeds, so I'll give a bit of a progress update on that. I think we're going to set up the steam weed control lance again, and we'll hit them again. So we missed a couple of weeds. So, hello Dan. Good. I wasn't actually videoing you there, I was videoing myself. See, look. You've been eating licorice.
Yeah.
Something I've been doing for a little while now is using canola oil as bar lube for the chainsaw, and interestingly it works really well. And the good thing about it, or the reason I'm doing it, is because quite a lot of bar oil ends up in the environment where it's used in chainsaws. So canola oil, of course, biodegrades. The fact that it's working so well as a bar lube in this chainsaw is interesting, because typically steam locomotives have a lot of total loss bearings on them where the oil is just lost. It's not recirculated like it is in the crankcase of an internal combustion engine. So if canola oil and vegetable oils can work quite well as a total loss lubricant, then I'm quite inclined to investigate the use for the steam locomotive, because it is a lot easier on the environment. I'll keep using it as a bar lube, but I've been using it for some time now. It seems to be performing just nicely. So this particular saw that I've been using originally started out using the proper mineral bar oil for it, but there's actually been a lot of wear on the bar, so I've just filed the bar to try and straighten it up, because it was cutting crooked and just stopping. So having transitioned to the canola oil, we'll see how long it holds its accuracy. Interestingly, mineral oils have tackifiers included in them to try and prevent the oil from being flung off the chain. But the canola oil, which doesn't have a tackifier in it, just seems to stay on the chain quite well. The chain is always slippery, whereas it can be quite dry with the mineral oil. And the great thing about canola oil is I think 2 litres is about $5, and the bar oil was about 1 litre for $20, so always nice to save some money. 4 weeks after making the application, there's a few weeds that have popped up in the interim, and some that we missed, but otherwise it's worked quite well. Some of the thicker grasses do seem to have come back. I'm not sure if we've missed them or whether they've just come back, didn't hold the steam on them for long enough. But all in all, it was quite successful for the first go, especially around here. So this was just full of grass before. It's knocked it back quite nicely. There was a plant covered by this piece of wood and it survived. So we'll hit that again. Well, it's working, but it's wasting quite a lot of steam, but we should be able to kill some weeds, at least. never been so far away from home. We're trying to reach some of these weeds out there. I don't think we're going to get that far, Well, that's it till next time. Thank you for watching, and a huge thank you to everyone who is supporting the project, whether that's by becoming a patron, or donating directly to the project, or just lending a helping hand. Thank you, I really appreciate it. If you haven't already, please subscribe, and do check out my page on Patreon. I'd love to have you on the team as a patron to help me on my mission to make transport sustainable, using the power of steam.